All right, welcome back. So we're going to do another Lagrange multiplier problem. I could do this one directly, but I like it better as a Lagrange multiplier. What the hell, we'll do it both ways. So we're going to optimize, we're going to minimize. Actually, let's write the problem as it said. And it says, find the point on the plane. I'm actually going to do it abstractly. AX plus BY plus CZ equals D that is closest to the origin. Okay, so when you get a problem like this and you aren't given the equations exactly, that's when you have to decide, well, what is the thing that I'm optimizing, minimizing, or maximizing, and what is my constraint? Now here, this one's pretty straightforward, I hope. We have to minimize x squared plus y squared plus z squared. Let's call that f of x, y, z. And our constraint is g of x, y, z is, of course, the equation of the plane. Okay, all right, so let's do it directly. Directly, what we're going to do is we're going to basically substitute for z. So if we do this directly, we solve for z, or x or y, doesn't matter. So z equals d minus ax minus by divided by c. And we're going to plug that in. So we're going to get some f of xy is x squared plus y squared plus d minus ax minus by divided by c squared. Okay, we're going to find the critical point analysis and do it like so. That one's a pain. Okay, so let's do the Lagrange multiplier way. So let's do it with Lagrange multipliers. Now this one isn't as symmetric as the other ones. Technically, yes, there is a symmetry we could exploit, but finding the symmetry, I've done it before, is more of a pain than just doing it with Lagrange multipliers without the symmetry. Okay? So, and you'll see what I mean by that because later on we're going to make things symmetric when we want them to be. So we're going to take gradient of f equals lambda gradient of g. So we get 2x equals lambda a, 2y equals lambda b, 2z equals lambda c. Okay, so lambda equals 2x divided by a, which also equals 2y divided by b, which also equals 2z divided by c. Okay, so we don't actually need to find lambda, but just we need to sort of see that the fact that it's the same is going to give us this. Okay? Okay, so now let's plug these values back in to the equation of the plane. Okay, so really what I'm going to do is I'm going to say, well, x is lambda a over 2 y is lambda b over 2, and z is lambda c over 2. Together with my constraint, okay, that means that we're going to have lambda over 2 times a squared plus b squared plus c squared equals d. Okay, that's of course when this is going to happen. So, um, sorry, d is equal to this thing. Okay, now let's go ahead and go back to x. Actually, sorry, before we do that, here we're going to find lambda. I know I said we don't need to usually, but this one it will work. It will help. So lambda equals 2d over a squared plus b squared plus c squared. Okay, now we can find our x. Okay, so x is 2ad over, oh, sorry, the 2's gone, ad over a squared plus b squared plus c squared. Y is bd over a squared plus b squared plus c squared. And z is cd over a squared plus b squared plus c squared. Okay? All right, and then we could plug that in to find the distance. The distance would just be this squared plus this squared plus this squared. Okay? All right. One more problem, and then that's it for Lagrange multipliers and optimization until you do your own problems.